Recently I was reading a book called Calculated Risks by Gerd Gigerenzer, hopefully I pronounced that right, which brings up the idea that statistics and specifically probability are often misconstrued and misunderstood. And so they compare probability and natural frequency, and I got very interested in how simplified the consideration was. So typically, kind of your standard probability math is this kind of strange formula here. The probability of A given B, that's what you have here. So A given B is the same as the probability of A and B simultaneously occurring or occurring together, divided by the probability of B happening totally. So basically, you have like B could happen within this kind of large capacity, but only a portion of that would also include A overlapping it. So Bayes' rule, to give an idea of disease and positive test. So if you have a disease and you go get tested, would it be positive, that sort of thing. We're going to use this in a moment specifically, but what it's saying is what is the probability that you have a disease if you get a positive test? And this starts getting complicated, or at least seemingly complicated. And in order to calculate this, you have to know the probability of the disease, which we're going to use breast cancer, which is a known probability. You're going to multiply that of the probability that you would get a positive test if you had the disease. So basically, that's going to be your true positive rate. So, if you have a disease, it would be true that it would test positive. And you divide that by the probability of the disease multiplied by the positive test, again, if you have the disease, so similarly to the top. But then, so that would be a portion of your positive test, right? Would be a true positive. But another portion of your test would be a false positive. So you have the ones that are actually accurately describing the disease, and you have the ones that are inaccurately describing the disease. So you're going to add to that the probability of not having the disease multiplied by a positive test. When you get to natural frequency, so this is how often it occurs given a population essentially, the math gets much easier. So given another test, typically we're going to use thousands because a lot of times your percentages are very low, so they might be include a decimal. So instead of using 100 and then throwing decimals in there, bump it up to 1,000 or 10,000 to ensure you're not having to deal with that. But you need a common denominator. So A in this formula, so the frequency here is going to be A divided by A plus B. A is going to be the number of people who test positive that actually have the disease, so that'd be a true positive. And B is going to be the number of people who test positive but don't have the disease. So that would be a false positive. So basically all the positives added up together. And really what this does, it's basically the same math in all honesty. But what it does is make things more intuitive. So instead of having to deal with all these, complex abbreviations for probabilities, you're just dealing with basic fractions. So with breast cancer specifically, it's often used because it's a relatively small number of breast cancer cases, but you have a lot of tests that are run. So you get a pretty good statistical pool. But then at the same time, it's also misleading because of the low prevalence. So the prevalence of the disease is 0.8%, so less than a percent. Converting that to a decimal, it's 0.008. The sensitivity, so basically how accurate the test is at picking up the disease, is 90%. So if you have the disease, there's 90% of the time it will tell you that you have the disease. Worth noting, if you this is the true positive essentially, right? The higher number this is, the higher the false positive rate is, which means that you're basically leaning the test to give you more positives. You want to make sure you don't miss someone who happens to have the disease and you tell them that they don't. So that's often a good thing. You're oftentimes going to catch more people who truly have it, but you're also going to scare people who don't because they're going to get a false positive. And then on the flip side of that coin, the specificity is 7%. What this means is if I don't have the disease, will it accurately tell me that I don't have the disease? So actually, should be inverted, I believe. But what this is saying is that 7% of the time I'm not going to have it, but it's going to tell me that I have it. So this is my true negative. So really it should be 93%, not 7%. I flipped that there. Um, Again, the higher this is, which means the more true we tell people that they don't have it, the higher number we're going to miss people who actually do have it. So there's kind of a balance between those. So if we enter this problem looking at it through kind of that probability lens, we got to kind of parse out some numbers here. So the probability that someone's got cancer, we already went over that's 0.8%, so turning that to a decimal, 0.008% of the population will have breast cancer. This little apostrophe on this next line is cancer apostrophe. That means not cancer. So that would just be the rest of the population. So 100% minus 0.8 is 99.2%, or as a decimal, 0.992%. What we have to kind of figure out is, okay, what is the probability of a positive test to begin with? And then what's the probability of a negative test to begin with? So for the positive test, we want all the true positives and all the false positives. So people who have the disease and test positive, and people who don't have the disease but also test positive. So to get those numbers, we're going to take the prevalence of the disease, which again is 0.008. That's that first number. We're going to multiply it by the likelihood of having the disease and testing positive. Again, if we go back, that was that sensitivity number. It was 90%. All right, we multiply that, but then we're also going to add the likelihood of not having the disease, but then testing positive. So there's 992 or 99.2% of the population remaining who don't have the disease, but 7% of those are going to test positive. So a small fraction of them will still show a positive test. So when we add those numbers together, we get roughly 0.076 or 8%. All right. And I also denoted this top number, the likelihood of cancer, the probability of cancer, is going to be the probability of A in our A given B formula. And then this positive test is going to be the B. Okay, so we've kind of designated those out. But we also need to know this negative test here. So now we got to figure out, okay, the true negatives are going to be people who don't have it. So again, that's going to be 99.2% of the population. And our specificity, which again I kind of inverted there, was actually 93%. So that means if they don't have it 93% of the time, it's going to tell them they don't have it. So I multiply those together. And then we go to the population that actually does have the disease. But remember, the test was only going to support 90% accuracy there, or sensitivity there. And that means there's another 10% that it's going to get wrong. So 0.008 was the prevalence of the disease, and that 0.1 is going to denote who in that group or what number in that group will still test negative even if they have the disease. So when we add those up, it gives you roughly 92%. Okay, so now our formula is what's the likelihood that we have cancer given that we have a positive test, and that's what that bottom line shows. So probability of A given B. So A, I denote as 0.008, right? That was the likelihood that we would have it. But remember, we have to kind of coincide the A and the B. So we're having, this is our population, our prevalence that has the disease, but we also got to account for that 90% sensitivity on the test. So you multiply those together, and you get 0.0072. And you're going to divide by the total probability of B, which was that positive test. So what we're trying to figure out is, okay, on the top, it's everybody who got a positive test who actually do have the disease. And on the bottom, it's everybody that got the positive test. And what that comes to is 9%. All right, so first off, should be interesting that number is so low, given that it's a 90% likelihood that it's going to catch the cancer if you have it, right? But if you test positive, it's only a 9% chance that you actually have the cancer. That's confusing. All right, you go through all this probability, you deal with all these probability ofs, you add them all up, you got to divide them all up, you got to multiply them out. An easier way to go about it is to look at it via natural frequency. And this is argued in that book that I referenced simply because it's a more intuitive way to think about things. And it's also a better way to explain it to different groups. So what you do is start by picking out a reasonable population. A lot of times it's 1,000 or 10,000. I think I mentioned that earlier, but it's because a lot of the percentages are small numbers or decimals, and increasing it over 100 prevents you from having to use decimals. And then your formula becomes A, which is everybody that it's basically the true positives, and divided by all the positives, right? So for every 1,000, we know that the percent was 0.8%, right? So if you multiply 1,000 by 0.8%, you get 8. 8 people out of this population of 1,000 will have cancer. Of those 8, we know the test will catch 90% of them. If you do the math, it's a decimal, but let's round it off. It's roughly 7 out of the 8 will test positive. So 7 out of the 8 who have cancer will test that they indeed have cancer. Well, you got 992 others who do not have cancer. Of those 992, we also know that 7% will still test positive. They will have a false positive. And if you do the math on there, multiply 992 by 7%, you have a number around 70. All right. And again, our formula was A divided by A plus B. If we look at that, that's 7, which is the true positives, divided by all the positives, or divided by the total of them is 77, roughly 1 out of every 11, or 9%. We get the same number. The math is way easier, and mentally, for many people, this makes more sense. Anyway, I hope that was helpful.